Please remember these key observations. Okay, this is very, very important. Please note down these observations. And then another thing that I wanted to tell you is that of course, so you should know what is the gain margin and the phase margin. Now I will take an example to illustrate that as the feedback factor reduces, your phase margin increases. So I have already defined what is the phase margin. So let us take a one pole open loop transfer function H of S. That means I have the feedback block diagram is like this. Beta over here, V out and V in. This is the forward path or the open loop transfer forward path open loop transfer function. We are putting what is the phase margin if beta equal to 1. A single pole system rolls off at a rate of minus 20 dB per decade in case of a Bode gain plot. Okay, this is the Bode gain plot. It will roll down. So DC gain of this is 20 log of A naught. Keep in mind it is log to base 10. Okay, so let me zoom in. So my sincere request to all the good students, please maintain your, those who have good marks, please maintain your integrity and all and continue doing well. Okay, do not help others, those who are not studying. Okay, DC gain is 20 log of A naught. Okay, omega GX gain crossover frequency is 10 log to base A naught decades away from omega naught. Does this make sense? So let's take a number. If 20 DC gain is, suppose it is 60 dB, that means A naught equal to 1000. Okay, that is there. Now what is the gain crossover frequency? If it is 20, it is going to be 10 to the power of log of A naught. Log of A naught is how much? It is going to be 10 to the power of 3, or it is going to be log of A naught decades. It will be 3 decades away from omega naught. Am I clear? So if omega naught is the 3 dB cutoff frequency, so it will be this exponent that much decades away, 3 decades away will be omega GX. So omega GX will be 10 to the power 3 omega naught. Any questions on this? Is this clear? For example, if 20 log of A naught equal to 20 dB, which is the DC gain in dB, then omega GX is 1 decade away from omega naught as shown here. Okay. If 20 log A naught is 40 dB, then omega GX is 100 omega naught as shown below. If 20 log A naught is 30 dB, omega GX is 31.62 omega naught. Okay. Thus phase at omega GX is given by how much? Tan inverse of whatever is the frequency divided by omega naught, because the phase of a single pole system is minus of tan inverse of omega by omega naught, where omega naught is the pole frequency. Now omega is the gain crossover. What is the phase at gain omega GX? Is you submit omega GX here, and this omega GX is nothing but this, and therefore you can get the omega GX as tan inverse of 10 to the power of log of A naught. Therefore phase margin equal to, phase margin is given by, this is the definition of phase margin. Okay, is this step clear to all of you? Okay, I hope so. Now what if beta equal to 0.5? What if beta equal to 0.5? Then the loop gain Bode plot is going to look like this. It is going to drop down by 10 log of 1 by 0.5, which is going to, this is going to be 6 dB if beta equal to 0.5. If beta equal to 1, then it is going to drop down by it is going to be 20 log of 0.5. So it is going to drop down by 0.1, suppose 0.1. Okay, it is going to be 20 log of 0.1. So it is going to be, this height is going to be minus 20 dB. Okay, so the loop gain plot, if due to beta equal to 0.5, is this. So there will be exactly 6 dB difference between them. Okay, so this plot is with beta equal to 1, therefore it is 20 log of loop gain is h, beta equal to 1. Where 20 log of beta h equal to exactly 6 dB down, so it is down by 20 log of a naught minus 20 log of 1 by beta. Okay, therefore omega gx beta equal to 0.5 is somewhere here. We call it omega gx beta equal to 0.5, and the omega gx beta equal to 1 is given by this. We have already seen this. Okay, omega gx beta equal to 1 equal to this. We already know this. Omega gx for any beta is going to be given by, you can put this in the exponent 10 to the power this times omega naught for any beta. Hence, for beta equal to 0.5, we get omega gx beta equal to 0.5. It is 0.5 times omega gx beta equal to 1. Okay, phase margin is going to be 180 degree minus tan inverse of 0.5 of this. Therefore, thus feedback factor reduces the, thus as feedback factor reduces, the phase margin increases. This number is going to reduce because this amplitude reduces. Okay, is this step clear to everybody? Any questions on this? Because 2 years back when I was teaching, a lot of people had doubts on this, so I especially made this set, these 2 slides, and I gave it as an example. Am I clear with these 2 pages? What I have done, just pure manipulation of these equations. It's just a graph. This graph, it rolls down. We tell how many, we can tell exactly in terms of this DC gain, where is this located. Once this drops, then this is the DC gain which is given by this, and therefore the omega gx for any beta will be 10 to the power of this DC gain omega naught. That's all we have done. Just like 20 log of a naught is the DC gain in dB. So our omega gx equal to 10 to the power of, we just take this one, log of a naught times omega naught. Omega naught is the pole frequency. Now, when I have any other arbitrary, this is beta equal to 1. If we for any beta, my gain is going to be 20 log of a naught minus log of 1 by beta. So this would therefore give omega gx for any beta, this is beta equal to 1, equal to 10 to the power of this exponent. Okay, let's call this as y, 10 to the power of y omega naught, and that's what we have written here. Now, if I put in this value beta equal to 0.5 for any phase margin, what do we get? We get roughly that the phase margin increases as feedback factor reduces. Now, as phase margin increases, what happens to the time domain behavior of the circuit? The time domain behavior becomes slower and slower. Any questions on this? Okay, so looks like everybody understood this. So I can give some interesting problems based on this. There are a lot of interesting problems. Now towards these last 5 pages, I have given 2 examples, okay, of finding the feedback factor going through the 7-step process. Okay, so please do it yourself. And if you have doubt, we can discuss this tomorrow. Tomorrow I'll set up a time, or why don't you guys set up a time tomorrow evening, 8 o'clock or something. You guys set up the meeting just like you did last time. So there are 2 example 2 and example 3. I am going through the, I first identify what is the feedback. Then we go through the 7-step process. Okay. Then I'm giving you another example here, and we go through the same 7-step process and do this. So I would suggest that you please work out this thing, this slide, these are already uploaded in your thing, and you should be good to, if you have any doubts, we can discuss that, because I don't want to go through this. We just follow the 7-step process of obtaining the feedback factor and the loop gain, and thereby the overall R in, R out, and the overall gain with and without feedback. Okay. With this, I think I would, this kind of wraps up the overall feedback chapter, negative feedback chapter. So this kind of wraps up the negative feedback chapter. If there are any questions, I would request that please ask me. Otherwise, we'll go on to the oscillator chapter and we wrap up the syllabus.